Hi guys, so today we'll be doing Leetcode question called constraint subsequent sums. So we're given an array, right? So we need to find the maximum sum of a subsequence. So what is a subsequence like? Let's take a look at this example. A subsequence is obtainable by deleting some element can be 0 from the array. Okay, so if we delete this, right, so we get a subsequence 10, 2, 5, 20, and the total is 37. So without the constraint, then it can be very easy, right? So what does this constraint mean? Let's take a look at this example. So if we delete all the element that are below 0 here, right? So we delete these three guys, right? So we get a total of 30, right? But it's not that easy because you see here the index of this guy is 0, index of this guy is 4, and if we get 4 minus 0, then it is equal to 4 and it's larger than 2, so it violates the condition of the problem, right? So if we're given k, then two adjacent element I and j, then j minus I must be smaller or equal to k. That is the constraint of the subsequent sums. Okay, so how are we going to approach this problem? We are going to do it using dynamic programming with a little bit of monotonic queue. So figuring out this DP algorithm is actually pretty easy, right? But the hard part here is how to speed up the DP, and we're going to do it using monotonic queue, and I will be explaining to you guys later. So here comes the DP part. So the description states that we can delete a number and it can be from 0, right? So like we can start from 0 or we can start from here, or here, right? As long as we satisfy the condition, which means two adjacent element, then the index, the absolute difference of the index is smaller or equal to k. So if we starting from this example, I have 10, 2 minus 10, 5, 20, then we actually can trying to start from each of these elements, right? Okay, so what if we trying to start from this element, and what's the maximum sum? Like it could be 20, right? What if we're trying to start with this element? It could be 25, right? What if we're trying to start with this element? Now is the hard part, right? We can connect to this guy, we can connect to this guy. So what do we choose? If we connect to this guy, then we get a total sum of 15. If we connect to this guy, we get a total sum of 10. So obviously then we will choose the bigger guy, right? So we get 15. Okay, coming to this guy, what do we choose? Like we can connect to this guy, but can we connect to this guy? No, right? Because if we connect to this guy, then we violate the rule. So this guy have an index of 1 and this guy have index 4, and the absolute difference between them is 3. So at most then we can only connect to the next 2 guy on the right of each element, right? So same logic, this guy is bigger, so we will connect to this guy and we get a sum of 27. Same for this guy, we like between these 2 guys, this guy is bigger, right? So we get, okay. So that's a DP part. So can you figure out the formula? Okay, here's the formula. DP I is equal to nums I plus max DP I plus j with j run from 1 to k, right? Okay, so for example with this guy, right, it could be equal to nums I is equal to 2 plus, if we take j is equal to 1, then we get this guy, right? And this guy is 15. If we j run to 2, right, and we get 25. So we get a total of 27 for DP at position I. Okay. Let me tell you, if we going to solve this using pure DP, then the time complexity would be O k multiplied by n, with k is constraint and n is a number of elements in the array. And if k is very large, like in the worst case possible, if k is equal to the number of element in the array, right, here in the constraint, then k still can be equal to the length of the nums. Then the time complexity could go up to k square, right, n square or n square. So let's take a look. Let's try to like solve it using pure DP. So I make the same mistake, right? As you can see here, copy to editor. Can you see? Okay. Quick. The hell? Okay. You can see in this case, and k is very large, so it will give a time limit exists, right? So is there any method that we can use to optimize, to speed up the DP, right? So I'm telling you that we can use a monotonic queue, right? Because we are like recomputing a lot of things when we calculating the DP at each element, right? At each index, for example. Okay. For example, at let me find an example. Okay. Here, when we get to this guy, right, we will be comparing the DP, this guy and this guy. So, but is there any point like using this guy, right? Okay, so coming to this index, right, we know that 25 is the largest number and it comes like after 20, so it will probably still be the span up, like it's going to be the candidate for this guy and also this guy, right? So this guy is probably not going to make it, right, because there's like a directly larger element that comes after it and it's going to span more, right? So this guy will never be the candidate for the second part of the DP, right? So what we be using is that we're going to use a monotonic queue to speed up the DP and get it to linear time complexity, right? Let me demonstrate it to you. So we will be maintaining a queue here. Okay. That's right here. First things, we at first position, then the queue is empty, so we will only be adding the nums I into it, so 20, right? After that, then we add 20 to the queue. Coming to this guy, 25, we add 25 to the queue. Now here's the tricky part, because 25 comes after 20, right? So do we even need to keep this guy anymore in the queue? No, right? So we will keep popping. If the current element is larger than the last element in the queue, then we'll keep popping it out, right? So we pop this guy out. One more thing. I'm sorry. And we need to keep when we append an element to the queue, then we need to append the index, right? For example, this guy 0, 1, 2, 3, 4 is 4. You see why we do it in a second. And we pop 20 out, right? So now we have 25 and we have what? 3, right? So coming to this guy, like, okay, so now rather than comparing to this and this, then we know that the current best candidate is this guy, so we're just adding minus 10 to 25 and get a result of 15, right? So now 15 is smaller than 25, so we will probably like going to add it to this queue, 25 and 2, right? Coming to this guy, right? Okay, so now we check the first guy in the queue. The index of it is 3, right? So the current index is 1. So we are probably this guy is still going to be relevant in this pass, right? Because the absolute difference between the index of the element, the first element in the queue, which the guy does come first, right, is 3, and the current element is 1, and it's still going to satisfy the condition, so we don't need to pop it out, right? Still going to keep it, so we get 2, add 25 to it, and we get 27. And we, okay, so now 27 is larger than this guy and larger than this guy, so we're going to delete all of this out of the queue, right? And get 27 1 here, right? So in the last guy we're going to just add 10 to 27 and get 37. So that's the use of the queue, right? The queue maintaining a list of candidates for the second part of the DP, right? And it's a monotonic decreasing queue. So we're always going to get the largest guy at the front. So, like, why do we need to keep the index here, right? You guys said. So, for example, at the last step, if this guy is not 27 but rather like 23, and we only at the 23, right? So rather than popping all of this, and we only going to pop this guy out, so and we 23, add this guy in, right? And then when coming to this step, right, we will be adding 10 to 25, which is at the top of the queue. But you can see that now this index is 0, this guy index is 0, and the top of the queue, the index is 3. So it violates the rules of the problem, right? So at the beginning of each pass, then we will check the index of the beginning of the queue to see if it still met the requirement. If not, then we just pop it out first, right? Okay, at this step, then this guy does not meet the requirement because 3 minus 0 is larger than k2, right? So we only going to the only thing left in the queue is this guy, so we get 10 plus 33 equal to 23 equal to 33, right? So that's the use of monotonic queue here. So let's try to reproduce it. Okay. Initiating queue, let's go to collection, EQ. So here, instead of another for loop, another next for loop, then we just do this, right? Nums plus whatever is like on the top of the queue, right? Q 0 1, yeah, Q0 Q0. If Q, only if Q is not empty, else then we just add 0 into it. And at the start of each pass, then we need to check if the index is like, if the top guy is still can be accessible, right? So if Q and Q0, we will store the index at index 1, minus I is larger than K. So we will pop it out, right? Okay. At the end of each loop is like where we're going to append the queue, right? Okay, so while q and nums I plus q 0 0 is like actually larger than q minus 1 0 q dot pop. So at the end we'll append nums I plus q 0 0. Okay, so I can pass this pass. Okay. So at each pass, then we're going to compare updating the result variable, right? So res is equal to max res, and then ep I, right? So go to return res. Int object is not iterable. Oh, okay. Yeah. We're going to append the like the value first and the dice, right? So I. What the hell? Let me see. Oh, okay. Okay, so why? Like, if we get like to this element and we know that the max element of the current best candidate is like -3, right? So is there any point connected to it? If it's going to decrease the total sum, right? So no, I'm going to be just on my own, right? So at any point, and if we're going to connect to something that's going to like decrease the total sum, then we're just going to cut it out, right? Like if you like smaller than 0, if the candidate is smaller than 0, then no, I will not be connected to you. I will be just on my own, right? So okay, let's give this quick submit. Okay. So time complexity of this is O of n. And state complexity is also O of n. Because we will be maintaining a queue, and in the worst case possible, like in this example, what the, okay, in worst case possible, then k is going to be equal to nums length, and it's going to be O n, right? So I hope that it makes sense to you guys. Thanks for watching, and see you guys later.